Alright, physics students, so today we're going to talk about uniform circular motion. And the situation that we've got is when an object is moving around in a circle. You can see we've got a nice circle here with different dots representing the object's position at various times. So uniform circular motion means that we're traveling at a constant speed along a circular path or around a circle. It also means that we are continually changing the direction that the object is traveling in. So you can see at different points the velocity vector is pointing in different directions. So since velocity is constantly changing direction, then obviously we have acceleration. I mentioned that in a previous video. That velocity is, when we consider velocity as a vector, then since it has magnitude and direction, if one of those two things is changing, then acceleration exists, because by definition acceleration is a change in velocity. So let's talk about that acceleration. So the acceleration itself is also a vector, which means that it has a magnitude and a direction. So here we'll draw another circle, just different points along the circular path. And something that we observed before is that these acceleration vectors are always pointing towards the center. Now, we didn't mention it before, but this acceleration vector has a name, and it's called the centripetal acceleration. And its direction, as I mentioned one moment ago, is always towards the center of the circle. We represent this by vector A and then the subscript C. So various points it's pointing directly towards the center. We know its direction, the direction of this vector, it's always towards the center, but what's the magnitude? Well, we don't know that. That's the primary question of this video that we're going to explore. And before we go there, just a quick note: at all points in this object's circular path, or at all times, the velocity vector is perpendicular to the acceleration vector. So if we were to draw the velocity vector at various times like this, we would draw it perpendicular to the acceleration, which the acceleration vector is, as I mentioned, is pointing towards the center, so it functions like a radius. And another way we can say that is that the velocity vector is tangent to the circle. Tangent not in reference to the sines, cosines, and tangents, the trig ratios, but tangent in the sense that it it touches that, it comes in contact with the edge of that circle just at that one point, and then continues to travel away from it. There's more technical definitions of tangent, but that's good enough for us right now. So this is our task for the rest of this video. We are going to find the magnitude of the centripetal acceleration for an object that is traveling in uniform circular motion. And to do that, we're going to need to draw a rather large circle, so I'd recommend you draw this really large if you're following along with your own notes. And we'll just focus in on 2 points as the object travels in that circular path from right here over to here. So we'll call this this point 1 and this point 2. So the object therefore would have velocity vector v1, which is tangent to that radius, or perpendicular rather to the radius, tangent to the circle, and velocity vector v2 at this point, once again perpendicular to the radius. We're going to do a couple of things here to actually find out what the centripetal acceleration is. Some of these things may not seem obvious, but this is how we get there. First thing we're going to do is extend this velocity vector out along the lines like that. Then you can see we've got object angle theta labeled up here. Next thing we're going to do is we're going to copy this velocity vector, vector 1, over here and label that angle phi. So you can see it's got the same magnitude, same direction, and totally okay for us just to move the vector there to see what's going to happen. Now, because we've extended this, the line containing this vector v2, we know that this angle right here is also phi, based on our geometry of parallel lines. That this angle right here is the same as this angle right here. Those are congruent because these are corresponding angles on parallel lines. The parallel lines are velocity vector 1 here. Both of those have the same slope, and it's being cut by this transversal v2. So a little bit of geometry come into play here. Actually, there's going to be quite a lot of geometry by the time we're finished. Next thing we're going to do is we're going to draw this dashed line. I'll show this in a few minutes, but this represents the displacement vector. Sorry, that's not exactly straight there, but you get the idea. And then from that line up to radius r, we're going to call this angle alpha, and this angle here beta. So you can see we already have one triangle which is formed. Sides r, r, and then these angles alpha and beta, and then the other angle up here is theta. And at this point we're going to have to just zoom in on this picture. So it's best just to redraw it so we can see what's actually going on. So once again, we've got the radius here, that displacement vector or displacement line going there. Our velocity vectors here extending, velocity vector 2, angle phi here as well. One thing I don't think we wrote down in the previous picture, but remember the velocity vector is perpendicular to the radius. That's also the case over here. I've drawn the perpendicular symbol here between the radius and the extension rather than over here, but of course obviously if this is 90 degrees, then over here this is also 90 degrees. We have alpha and beta, and this inside angle from vector 1 up to this dashed black line here connecting those to the displacement line, we're going to label that as 90 minus alpha. And the reason is, obviously, if you look at the whole large angle right here, that's 90 degrees. This portion up here is alpha, so obviously what's left over is the complement, 90 minus alpha. And the same thing over here between the dashed line, which contains velocity vector v2, and the displacement vector, that dashed black line. That's going to be labeled as 90 minus beta, because if you look at the whole large angle, that's 90 degrees. It's labeled right there. This portion is beta, so this right here must be whatever's left. So 90 minus beta. So keeping that in mind, you've got it on your screen, but I'm going to write over here. One thing that we can say is that 180 equals 90 minus alpha plus 90 minus beta plus x. We're going to label this angle right here x. So looking right here at this triangle that we formed, this angle plus this angle plus this angle all must equal 180. That's some more geometry there for us. Thinking back to that original first triangle, or excuse me, pardon me, focusing in on this angle here, we can see that angle x and angle phi are supplementary. Together they form a linear pair. So 180 equals phi plus x, and I've written this in such a way that you can obviously see that this sum right here must equal phi. So phi must be the same as 90 minus alpha plus 90 minus beta. A little bit of algebra, combine those 90s, so we have 180 minus alpha minus beta must equal phi. Now we're going to go back to that original triangle and recall that theta, which was at this point it's way up here, is equal to 180 minus alpha minus beta. Here's that triangle. If at theta, alpha, and beta, obviously all three of those added up together equals 180. So the conclusion that we can arrive at is that phi must equal theta, since you can look vertically here, they're both totally lined up. Phi is 180 minus alpha minus beta, and so is theta. So this angle right here, which is between the two velocity vectors, is the same as the angle that we had between the two radii. Just have that labeled as equals theta. Also, and this is all going to come back to what the magnitude is. You guys just take my word here on it. So I'm going to redraw that velocity vector 1 and velocity vector 2 that we put at the same point. And sorry, this is not completely to scale here, but you get the idea. If we were to draw negative vector v1 at the tip, or the tail rather, of v2, then it would be going up and to the left, obviously, since it's negative. And then if we connect the beginning of v2 to the end of negative v1, then we would have v2 minus v1. And then, like I said, this is horrifically off. But the point is that that vector right there corresponds to this third side of the triangle, v2 minus v1, which, as we discussed in previous episodes, that's equal to delta v. As noted just a moment ago in the previous slide, that angle, which we called phi, is also equal to theta. And this is where we get what we get from all that. So now, the first triangle, which had theta on one side, or as the angle, radii on two sides, and this other triangle, which we formed from the two velocity vectors, has theta there and delta v right here. Those two triangles are similar by side angle side congruence, or sorry, side angle side similarity. Remember, that's yet another geometry concept, that if two triangles have congruent sides, or sorry, similar proportional sides and a common angle, then the entire triangle are similar. And similar triangles, you can write proportions for them. So delta v, the side across from theta, over one of those v's, since those are the same velocity vector, is equal to the displacement vector. You say, wait a second, you never mentioned that was displacement vector. Well, actually I did technically, and remember, displacement is just the distance from where you end to where you begin from. So that's displacement vector right there, divided by r, which is one of those sides. So we've got this side over one of those two congruent sides of this triangle is equal to the proportion of the side across from theta divided by one of those sides. Then from there, we can replace that magnitude of the displacement with v delta t. A little note here as a reminder, remember the displacement is velocity times the change in time. Then, a little algebra, we're going to divide both sides by delta t. So that delta t over there reduces completely, and we have delta v over delta t. At the same time, we're going to multiply both sides by v, canceling out this v. Now we have another v over here, so we have v squared in the numerator over r. I'm going to fix that r, make it look more r-like. And finally, delta v over delta t, we've already discussed that's the definition of acceleration, is change in velocity over change in time. And looks like we've arrived. This is what we're going for, what we've been shooting for. This right here, this value, is the magnitude of the centripetal acceleration. It's whatever the velocity of the object is squared, its magnitude squared, divided by the radius. So it's a really long proof for a very simple but very powerful formula, and we'll do some examples of that and how to use this formula in class. Thanks for watching.